Yeah, so thanks for the invitation and the introduction. So today I'll talk about some recent work about something that I guess is really motivated by probability and Markov chains, which is what I study. But it has a lot of connections to number theory, like analytic number theory and I guess combinatorics. And I think maybe the goal of the talk, more than presenting a bunch of proofs, I really also want to sort of advertise that there's a lot of interesting questions in this direction. Um, and I know some people in the audience have already studied this stuff, so maybe it's not needed. But I really do think there's some interesting connections that are worth looking into. Okay, but before I talk about exactly what I'm studying, let me just give a little bit of motivation for why I care about the problem. Okay, so I don't know exactly how familiar everyone here is with probability theory, but the stuff I'm talking about is fairly simple. So here I'm going to use xn to denote a Markov chain. I'll assume it's ergodic. I mean, basically that means that it it's the assumption that you need so it converges to some stationary distribution that's unique. Okay, so it's sort of classical that the Markov chain will converge to something called the stationary distribution. And the question that a lot of people care about is how long does it take for this convergence to occur? Okay. So one reason that this question is very interesting is that Markov chains are actually used in practice. So one very useful fact is that you can sort of come up with a Markov chain that converges to some stationary distribution you want to sample from, even if you can't sample from the distribution itself. Okay, so maybe it's computationally infeasible to sample from some hard probability distribution, but you can come up with a Markov chain that'll converge to it. And so this is one way to sample. Okay, so I mean, of course, what I'm going to talk about today, isn't really directly relevant to that, right? Like nothing I'm going to talk about will ever be useful in practice. But just from a theoretical perspective, this is why people really care about studying what's called the mixing time of Markov chains. But actually today, so I mean, this question is still mostly unanswered, right? Most Markov chains that people actually run on computers and stuff, we have no idea how long it takes for them to converge. Okay, so just in some sense, these algorithms, you kind of just run them until it seems to stop changing, and then that's sort of when you say that it converges. It would be nice to have theoretical guarantees. But anyways, I'm not really going to focus on that today. I want to sort of look at a slightly different question, which is suppose that we have a Markov chain, that converges. Can we make it run faster? So of course, this would also be very useful from a computational standpoint. Again, nothing I'm going to say really has any relevance directly to actual applied problems, but I think it's an interesting question to look at. So let me just talk a little bit about some previous work that has studied this problem. So there's this work of Alon, Benjamini, Lubetsky, and Soden from a while ago. So they studied something called non-backtracking random walk. So basically, this is a random walk, let's say on any graph, but they were looking at expanders, where you can never go back to where you started from. Well, from your previous step. So essentially, when you take a step, you don't just sort of immediately go back to where you came from. There's also this work of the series of works, I should say, by Ding Perez, Herman, and then Herman and Perez. They basically studied perturbations of random walks and graphs. So you start with some edge weights, and then you maybe perturb those edge weights in some way. And so both of these works, they showed that you can speed up the walk, but the speed up is fairly insignificant. So it's by some like logarithmic factors that are not particularly relevant. So maybe something like going from n to n over log n or something like that. The second set of works I want to talk about. So there's this work of Bordenov, Chu, and Zhang, and then Chatterjee and Diaconis. Um, so what they studied is basically you start with a random walk, and then you apply a permutation between steps of the random walk. Okay, and the idea is that if the permutation is anything like a random permutation, so it's very vigorous in its mixing, then then this should definitely help speed up the walk. And indeed, this work of Chatterjee and Diaconis, which, by the way, so this work is the one that's most relevant to what I'm going to talk about. So I'll talk about the details a bit later. Um, but they were basically able to show that you significantly speed up the mixing. So the time it takes to converge could go from something like n to log n, where n here will generally denote the size of the state space that we're dealing with. And finally, there's also some related work of Hermann, Sly, and Susi. So they basically studied what happens if you start with a random walk on a graph and you add a random perfect matching. Okay, so of course, this is quite similar to doing a random permutation in some sense. Okay, so this is just sort of to give you an idea of sort of what's been studied before. Are there any questions about any of the motivation before I move on? Okay. So if not, then let me talk about some more details of what I'm studying. Okay, so the sort of measure I'm going to use to determine how close I am to stationarity is the total variation distance. So everything I'm going to deal with is going to be on finite state spaces, and so you can think of this as just the L1 distance between the like where the distribution of what I'm currently at and the stationary distribution. So I'll use P to denote a Markov chain um, on a state space X, and the stationary distribution for me will always be denoted by pi. And I'll use this notation to denote the probability of going from X to Y in n steps. Okay. And so then we come to this important definition of the mixing time. So what is the mixing time? So we define this measure of how far we are from stationarity, and it's a worst case measure. Okay, so what it says is we start from any initial state X. We look at the distribution of the random walk after n steps, and we compare that to the stationary distribution in total variation distance. Okay. And then the mixing time is basically the first time at which this distance drops below epsilon for some parameter epsilon. Okay, so maybe a couple comments. So the first thing is that, of course, we could look at other measures of distance. So, and people do. So there's, L2 distance, there's something called separation distance, but I'll focus on total variation distance, which is actually very natural from a probabilistic perspective. The other thing maybe I'll mention is that, maybe you're familiar with something called the cutoff phenomenon. If not, it doesn't matter because it's not relevant to my talk. But this is kind of a very, famous thing that occurs in some Markov chains, where the mixing time to leading order at least basically doesn't depend on this parameter epsilon. Okay, so what that means is that there's sort of a sharp threshold for convergence to stationarity. And this is something that's very interesting to study, and it's a little relevant to some related works that I'll mention, but I won't be able to get something quite so sharp. Okay, so now let me introduce the model that I want to study. So I'll use P for the transition matrix of my Markov chain, and I'm going to assume that it has a uniform stationary distribution. Okay, so I mean, I'll mention later, some special case where it can be relaxed, but in general, I'll assume that pi is always uniform. And F is going to be some bijection on my state space. So I'm going to define now a new Markov chain, which is given by first applying F and then taking a step from P. Okay. So hopefully that definition is clear. I mean, please ask me if you would like it clarified. But maybe let me give you an example of what I mean. So if we look at the state space Z mod MZ, so the integers mod Z, for M odd, we could take any random walks. So let's say, the epsilon I are maybe Bernoulli, a half. Okay, so they're either 0 or 1 with probability a half. Mod P, obviously, and the bijection is multiplication by 2. Okay, so this would be an example of what I'm talking about. Any questions about the setup here? Okay, so if not, let me now talk a little bit about this work of Chatterjee and Diaconis. So what they showed is that for most bijections, the mixing time of this model that I described is logarithmic in the size of the state space. Okay, so let's just look at a simple example. The one that I was talking about before. So let's consider lazy simple random walk on the cycle of size n. Okay, so I mean, of course, it's basically this. By lazy, I just mean that you stay where you are with probability a half, say. And otherwise, you go either +1 or -1 with probability a quarter, maybe. I mean, of course, the exact numbers don't really matter. It's a pretty robust result. And so what the result implies is that if we uniformly pick a random bijection, and by this, of course, I mean at the very beginning, once and for all, fix a uniformly random bijection and then use the same one at each step, right? We sort of have a fixed bijection that defines the walk, but the randomness is sort of like the randomness of the environment, say. And then with high probability, the mixing time is asymptotically log n, okay? And of course, this is much, much faster than the one you started with. So simple random walk mixes in order n squared time on the n cycle. And so this is what I mean by speeding up the random walk, right? We go from polynomial to logarithmic in the size of the state space. Okay, so I'm not really going to talk about the details of the work. I mean, it's a little more technical, but I think this gives you an idea of what they showed. Two comments. So first of all, it's really, really easy to come up with bijections which don't speed up the mixing, right? So, I mean, identity permutation, obviously, but any bijection that sort of preserves the graph structure of the cycle, I mean, it's really easy to see that it's not going to speed up mixing. So like a reflection or a rotation. Also, any bijection which only mixes up a finite number of sites. I mean, that also definitely won't help you. The reason for this n squared mixing time is that the random walk won't like even be able to get to the other half of the cycle before n squared time. And so if you just do, fiddle around with a couple of sites, that's not going to help you. So really the heuristic is that you want some permutation which looks random. And the effect of the permutation is that it sort of mixes up the graph structure so much that the resulting graph looks random, right? And that's sort of what causes the speed up. So another thing is that it's really hard to sort of, if I give you a permutation, it's really hard to tell whether it actually helps or not. So in general, there's no um, real way to determine, like, given some permutation, will this like speed up my walk in a significant way or not? Okay, so this is sort of what I want to study. Okay, so this sort of motivates the problem of finding sort of explicit examples of random walks and bijections where we do get speed up. Okay, and so one reason maybe that we would like explicit examples is because, as I said, this work is motivated by applications in some high level sense. But if you think about it from an applied point of view, it really doesn't make sense to expect to sample from a random permutation. If you can sample from a random permutation, you can just sample a random element, right? I mean, it's strictly harder to sample a random permutation. And so, really, you don't want a random permutation. You want some very explicit permutation that you can do on the computer. And you would like that to speed up mixing. And that's sort of what we would actually want. And so finding, explicit examples, I think, is an interesting problem. Okay, so let me talk now about this work or this model, this Chung-Diaconis-Graham process. So this, by the way, this is actually the work that sort of motivated the work of Chatterjee and Diaconis. So the point is that, there were some examples out there already in the literature where the speed up does occur, and they sort of, asked whether this happens in more general settings. So let's go back to the Markov chain I mentioned earlier, this walk on the integers mod m. Just for, to be explicit, let's take our epsilons to be independent and uniform on -1, 0, and 1, okay? So as I mentioned previously, this fits into our framework with the bijection multiplication by 2. So this model was introduced by Chung-Diaconis and Graham in 1987, and I guess they were motivated by pseudo random number generation. So I think these, I guess like linear congruence generators or whatever. So this model is actually really, really interesting. And so I think, you know, even from like a number theoretic point of view, um, so there's this work of Eberhard and Varjou, recent work, where they showed that for most m, in some appropriate sense, the mixing time is asymptotically c log m for an explicit constant c, which is related to some asymptotic entropy of this random walk. Okay, so the point is that you can sort of get a lower bound on the mixing time through entropic considerations. And actually, there's this heuristic in sort of this field that for random instances, this sort of entropic like lower bound is actually the correct mixing time. Now, of course, there's nothing random about this example, but I guess there's also this heuristic that sort of a lot of examples coming from number theory sort of behave in a random way. Um, so I think their work is very interesting because it's actually not true for all m. So actually, in this original work, 1987 work of Chung-Diaconis and Graham, they had already noticed that for infinitely many m, this mixing time is of order log m log log m. Okay, and actually the example they gave is when you take m to be of the form 2 to the k minus 1, um, then you actually need more than logarithmic time. Okay, so there's something very interesting going on in this example that's still not completely understood. There's also maybe I should mention this other work of Rilliard and Varjou, where they study sort of kind of this the same setup, and they relate it to this conjecture number theory called sorry if I butcher this name. I think the Lemaire conjecture or something like that. Lemaire. So I'm not an expert in number theory by any means, so I'm not too familiar with this connection, but I think it's quite interesting. So let me also mention that this two of course is not particularly relevant. You can prove similar results for many other linear functions, but obviously again not all linear functions. So the identity function is not going to help you. Um, and so this gives kind of what I asked for. This gives lots of examples where the speed up does occur. So any questions about this slide? Okay. So if not, then let me move on to what I want to talk about, which is sort of a more general setting. So here I'm going to restrict myself to finite fields. Okay. So the reason is, I mean, eventually I'm going to want to apply something like the Weil bounds, and we're going to want to work in the field setting. So I'm going to consider a random walk. But now the bijection, instead of being a linear function, it's going to be a rational function. Okay. So I mean, of course, a rational function, maybe it's not defined everywhere. So you can fiddle around with like a finite number of values, say. So by almost rational, I just mean that it agrees with the rational function up to let's say a bounded number of points. And of course, I mean, every function on a finite field is a polynomial function, and so I want it to be low degree. Okay, so I'm going to get sort of quantitative bounds where the constants depend on the degree, and of course I don't want that to blow up. And also, uh, an assumption I have to make is that it's not linear. Okay, so this is again some kind of technical assumption. I mean, the result is already known for linear functions anyway. So whatever. Just to give you some examples, you can consider f of x equals x cubed when p is 2 mod 3. So this is an example of something called a permutation polynomial, which is, I mean, it's a permutation that's also a polynomial on a finite field. And you can also consider f of x equals 1 over x when x is not 0, and f of 0 equals 0. Okay, so this is an example of something that's almost a rational function. And then for simplicity, we're going to make the chain lazy by staying in place with probability a half. Okay, and basically this assumption is just to avoid periodicity issues. This can sort of be relaxed a bit, but let's not worry about that too much. Um, okay, and so what is the main result I'm going to talk about? So essentially in this setup, so the model that I just defined, I'm able to prove a mixing time bound which is almost linear. Okay, and this p to the delta can be replaced with some log power. Um, but anyway, so a couple comments. So first of all, this provides again a lot of examples where speedup does occur. Now the speedup is definitely less significant than before, right? So before we went from polynomial to logarithmic. Now we go from sort of n or p squared, I should say, to like p to the 1. But it is still significant. And I would say the nice thing about the result is that it applies to sort of a whole, a wide variety of functions, to all rational functions. Now, of course, the lower bound that one can obtain is still, order log p. And so this does leave a very large gap. Okay. And as I'll mention in a couple of slides, I have some reasons to expect that log p is the correct answer. And I think this is something that would be interesting to study. Let me also say that there's sort of an implicit constant. And so this implicit constant depends only on epsilon delta and the degree of f. And if it's a rational function, I mean the degree of the numerator and denominator. And so you can vary f as you take your asymptotics. Which is another nice thing about this result. It actually does give quantitative bounds. And maybe I should also mention that the constant is actually explicit. Like it's pretty reasonable. Okay, so any questions about the statement of this this theorem?
So there's a question in the chat.
Ah,
what is epsilon here?
yeah. So yeah, maybe I should have reminded you. So and maybe I should also apologize for the clash of notation. So the epsilon is the parameter epsilon in the mixing time. I mean, okay, to be quite honest, the epsilon only appears, I think, in the low order term anyway, so it doesn't really matter. But there's this epsilon parameter in the mixing time which controls like how close you need to be to stationarity, before you say that you're close, and that's the epsilon. So it's not this it's not this epsilon, which is the random walk steps. And any other questions?
Can I ask a question? So is there any known example of a bijection that doesn't speed things up and there's not an obvious reason why it doesn't? So like you listed, yeah.
Yeah, I mean, I guess it sort of depends on what you mean by obvious. But yeah, I haven't thought about it too much. And I'm not sure. Yeah, I mean, really depends on what you meant by obvious. Yeah, I guess the heuristic basically is that random, like really it should look random. So in that sense, maybe not, but yeah, I'm not sure. That's probably an interesting thing to think about. Yeah, and that also gets to the question of like exactly which permutations, like what sort of structure you need to be able to guarantee this sort of thing. So there's a couple of sort of I think things that like are kind of so you generally don't want things that have like low order, for example. But again, that's not a hard and fast rule by any means, as I'll explain later on. Yeah. Okay, so yeah, so if there's no more questions, let me move on to some related results. So actually, when we have this function f of x equals 1 over x, which I mean has very low order, so it kind of exactly contradicts what I just said. You actually get a much sharper result. So we're able to get a log p mixing time bound. So this is joint work with with Hui Pham and Max Xu, who are both also students at Stanford. And so we're able to show that for this random walk, we actually do get the same logarithmic bound, which is a lot sharper. So actually, I'm not going to talk about the proof of this result too much, but let me mention where it comes from. So actually, this result is, I mean, the hard work of this result really is this kind of, I guess, well-known work on well, I call it mixing on SL2. I think maybe for the audience here is like the spectral gap of Cayley graphs on SL2, right? So there's this work of, I guess, Selberg, Bourget, and Gambert. I mean, there's probably a whole bunch of people here that I should have listed, but didn't. Where it's kind of well known that like what like generating sets give you a Cayley graph on SL2 with a constant order spectral gap, and that immediately implies logarithmic mixing time bounds. And the point basically is that I mean, this walk, as I said, is not exactly related to walks on SL2, but if you squint a little bit, close your eyes maybe, if you just imagine 1 over x, I mean, that's a linear fractional transformation, right? And so if you, instead of working over fp, you work over p1, then it really is the quotient of a random walk on SL2. And so our work basically is to sort of relate the walk on fp to the walk on p1, and then use the fact that that SL2 acts on P1 of FP. Okay, and so it's sort of well known that the constant order spectral gap descends from the walk on SL2 to the walk on P1. And there's a couple more technical annoyances, but that's the idea, and so this is why one reason why maybe for more general random walks that I'm considering, it's also log p. But of course, this proof method definitely will not extend to the more general random walks. Okay, so any questions about this result? Okay, so if not, let me mention a third result that's related. So I defined the random walk I'm studying with bijections, but of course you don't have to use a bijection. The random walk is well defined, even if f is not bijective. The thing is, the stationary distribution won't be uniform anymore, right? I mean, the whole point of using a bijection is that it preserves the uniform distribution. And so in general, I mean, the stationary distribution is kind of intractable. Like, you have no idea what it even is. And so it'd be kind of hard to study the mixing time. But it turns out if p is 3 mod 4, then for the function f of x equals x squared, you actually can get the stationary distribution. So it's given by this explicit formula. And where does this formula come from? I mean, it comes from quadratic reciprocity, right? So it's actually pretty easy to check that this is the stationary distribution. And so I can still prove this almost linear mixing time bound. But on the other hand, when p is 1 mod 4, even the stationary distribution is kind of unknown. And this is also something that I think is a little interesting. So, if I have time at the end, I'll say a little more about this. But the point is that when p is 1 mod 4, it seems like the walk behaves almost like a random walk. Sorry, a walk on a random graph, but subject to certain degree constraints. Okay, so by quadratic reciprocity, you can sort of count the number of vertices with given in degrees and out degrees and so on, and slightly more. And the point is that, subject to those constraints, the graph kind of looks random. And there's some sort of very concrete things I can say about that maybe at the end. And so I think this is also a problem that's maybe worth looking at, because again, it's one of these examples where this number theoretic construction gives you something that looks completely random. Okay. So let me now turn to the sketch of the proof. So I'll spend most of my remaining time, talking about uh, the sort of ingredients. I won't go, too much into depth, but so the idea basically is reduced to some sort of spectral, computation. So use Cheeger's inequality to reduce to sort of counting, edges in some graph or counting solutions to some equation. Um, then you sort of, you know, could count the edges in sort of two scenarios. So there's one scenario where your S, the set S, is sort of has a lot of structure. So in particular, it's the union of a few sort of arithmetic progressions. And there's another scenario where the set S isn't the union of a few arithmetic progressions. Um, when it isn't, you can kind of use the structure of the random walk and some sort of elementary combinatorial arguments to sort of directly get a decent bound. And then when the set S does have this structure, when it is the union of few arithmetic progressions, use techniques from analytic number theory, so in particular exponential sums, to handle the counting of these solutions. Okay, so first, let me talk a little bit about the first step. So what are these spectral methods? So the point is that when my Markov chain, let's say, is symmetric and lazy, right, then the eigenvalues are all real. I mean, it's a symmetric matrix. In the special case when pi is also the uniform distribution. Um, and so all the eigenvalues can be ordered, and they're all bigger than or equal to 1. Then the quantity 1 minus lambda 2, so the second largest eigenvalue. So this is called the spectral gap. And this controls the mixing time. So there's this kind of well-known bound called Cheeger's inequality, which bounds the mixing time in terms of 1 over the spectral gap and this log n thing. Okay? And so this is what I'm going to use to control the mixing time. Okay, so right. Okay, sorry. So I guess maybe Cheeger's inequality also includes this. So for simple random walk on a d regular graph, say, the Cheeger constant, also sometimes called the bottleneck ratio, or maybe the conductance, or whatever, is defined as this quantity. So you count the number of edges from a set S to its complement, and then you divide by d times sort of the size of S or S complement, depending on which is smaller. And then you take the minimum over all non-trivial S. Okay, so I mean, S cannot be empty or the entire graph. Okay, so the point is that in this setup, the Cheeger's constant controls the spectral gap. Okay, so up to a power of 2, it's of the same order as the spectral gap. And so to show that that the random walk mixes quickly, you basically just need to show that the Cheeger's constant is large. Okay. Now, there's a couple assumptions that I stated in these slides that aren't exactly true in my setup. So I said reversible or symmetric, and I said simple random walk on a deregular graph. I mean, all these assumptions can be relaxed, and I think it's pretty well known how to do these things. So I'm not going to get too much into the details of that, but there is a little bit of work that goes into that. Okay, so I guess maybe in this audience, this stuff isn't completely foreign, so I won't say too much more about this. But any questions I can answer? Okay. So if not, then let me talk now a little bit more about what I mean by structured versus unstructured. So okay, so I mean an arithmetic progression is just some set of the form x plus 2, x plus 4, and so on. For a 2 arithmetic progression, I would say. And of course, it wraps around because we're working about P. Okay, so any set has a unique decomposition into sort of maximal 2 APs, right? So I mean, you can do this by like a greedy algorithm. So all this is what I mean by a decomposition into 2 APs. And the point is that, like I sort of said in the sketch, we're going to sort of use 2 different methods to bound the number of edges from S to S complement, depending on whether S has few or many 2APs in the decomposition. Okay. So in the unstructured case, when S has many 2APs, what do we do? Well, the point is the following. It's kind of actually a simple observation. So suppose we have some point X and we want to count, in S, and we want to count the number of edges. We look at y minus 1 and y plus 1, where y is sort of, it's basically so the point is that, sorry. I think I reversed my letters. So y is going to be, sorry, x is going to be something in S, and I'm going to look at f inverse of y. And so, because x is f inverse of y, after applying f and adding or subtracting 1, we're going to move to either y minus 1 or y plus 1, right? And so now we can ask ourselves, if x is in S, if y plus 1 belongs to S complement, then there's sort of an edge going from S to S complement. And if y minus 1, sorry. Yeah, right. So, sorry. The point is that y plus 1 and y minus 1 cannot both be an S complement. Okay, so what we're going to assume is that, because we have many 2APs in the decomposition, right? Each 2AP means that there's an element, I guess, y minus 1, where once you add 2, you leave the set, right? So the point is that once you're in this situation, you can find an X which maps to both y plus 1 and y minus 1. And this guarantees that you have an edge going from S to S complement, okay? Yeah, so sorry about that. I think I got a little confused by what I wrote. But the point is that this sort of combinatorial argument guarantees that every 2AP in your decomposition gives you an edge from S to S complement, okay? And so this means that if you have many 2APs, you have many edges. Okay, yeah, sorry again. Any questions about that? I kind of butchered that a bit. Okay, so if not, then let me move on to maybe the more interesting situation, which is when we do have many 2APs. Okay, so obviously, counting edges is equivalent to counting solutions to the following two equations. And, for the purposes of counting, it suffices to just look at one. So for a general set S, there's no real way to estimate the number of solutions to these equations. But the point is that when S is the union of a few 2APs, S and S complement, I should say, one can use techniques from analytic number theory. So again, I mean, everything on this slide is probably familiar to most people here. So the point is that you write your set that you're trying to count, which in this case is the number of edges from S to S complement. And we can get a lower bound by just counting the number of X in S, where f of X plus 1 is in S complement. And we can sort of expand this into a bunch of exponential functions, right? And now the point is that the alpha equals 0 term in this sum contributes sort of what you would expect from a random sum. So it contributes the size of S times the size of S complement divided by P. And we'll split off the rest into an error term, okay? And that's sort of what we're going to try to control. And it's kind of easy to see that if we can control the error term, then a lower bound coming from the main term is going to be more than good enough to give us what we want. Okay, so how do we control it? So again, maybe this is maybe familiar to a lot of people in the audience here. So the error term is an example of something called an exponential sum, which is kind of heavily studied in analytic number theory. And so there's actually lots of techniques to bound these things. These are pretty well studied. so the sort of methods I'm going to use are to apply the Weil bounds. And there's this sort of argument. I mean, there's this work of Browning and Haynes. So they actually essentially studied the case that I care about in when f of x is 1 over x. Um, and essentially the argument is to sort of take the Weil bounds, which are an estimate for complete exponential sums, and sort of turn them into an estimate for incomplete exponential sums when you're summing over a disjoint union of two APs. Okay. And the reason that you need to assume that f is a rational function is basically because we want to apply the Weil bounds. Okay. So how do we control the error term? So so I'm going to use R to denote the error term, and by some simple calculations, you can control R by the following sum. So you sort of have two parts here. You have this sum over S and sum over S complement, where the sum over S, you have the F, and the other sum you don't. Okay, so one of them is a linear exponential sum, and the other one is a nonlinear exponential sum. And the point is to sort of control them separately. So what are the types of bounds that I get in the linear and nonlinear case? So in the nonlinear case, we get a bound of the following form. Okay, so essentially you get some sort of square root savings in these bounds. Okay, so if you just apply so I hope I mentioned this earlier. So J is equal to the number of two APs in the decomposition of S. Right, so the point is, if you just apply triangle inequality, you're going to get J times the bound you would get for a single interval. And you get this savings of J to the ½ and that turns out to be what we need. So again, the key input is the Weil bound, and then the argument mostly follows this work of Browning and Haynes. So I think really from a sort of analytic number theory perspective, maybe the result isn't really unexpected, right? I mean, it's I think something that uses mostly standard ideas from the literature, I think. So any questions about these bounds?
So how large should we think of J as being? Like what is the threshold for like having a lot of two APs?
Yeah, that's a good question. So the threshold basically, I mean, it depends on S. You want to take a look at something around I think this. So I mean, it's going to be some power of P. So it's definitely going to be significant enough that this bound will give you an improvement. Yeah, I guess there's also this log L thing, but I mean, that's also not particularly important.
Okay.
Yeah, I mean, it's a little, okay, the actual argument is a little more annoying. I mean, you also have to separately deal with the case when S is really small. The point is that when S is really small, the ratio is going to be big anyways, right? Because, I mean, you're dividing by the size of S. And when that is small, you don't really have to worry about anything. Yeah, so, okay, so, maybe another thing I should mention is that I'm also reducing to the case when all these arithmetic regressions have the same length. I mean, the reduction of that, I think, is also a very easy argument, like kind of by some averaging arguments. You can show that if you have a set which decomposes into two arithmetic progressions with a given average length, then you can find a comparable number with like maybe half the average length, all of the exact same length, right? So it's pretty easy to reduce to that case. Okay, so if not, then let me move on to the linear bounds. So the linear bounds, it's also kind of the same thing. We get this sort of square root savings. So I mean, the case of an interval, I think, is very well known. I mean, it's an arithmetic progression, so there's kind of easy ways to get bounds for an interval. And sort of the point is that, when you're dealing with a disjoint union of intervals, you can sort of, think of it as you're sort of summing over two scales, right? So you have this, these sort of intervals which are kind of spaced around, and the intervals are all spaced at least the length of the interval apart, because the arithmetic progressions are disjoint, right? And because of the spacing, you can sort of imagine that when you sum, there's sort of two different sets of like oscillations going on, and they sort of interact at different scales, so you can sort of average over one before you then sum over the other. So really the argument boils down to sort of blocking your summation into like a whole bunch of blocks, and then summing over blocks and then summing over the rest of it. So I don't really want to get too much into the details. I think this also is not shouldn't be too surprising. Okay, so the point is you get the square root savings. And these two bounds, the linear, the nonlinear estimates are enough to give you what you need. Okay. So maybe this is just to summarize. So the final bound you get is something of the form j times p to the half times some log factors. And for j, l, and l prime sufficiently large, you get a good enough bound. Okay. So and that completes the argument. Okay, so yeah, I mean, like I said, I think from maybe an analytic number theory perspective, I don't think that these arguments are maybe so surprising or, too interesting. I mean, of course, this also implies something about counting solutions to some equations, but I don't think the proof is particularly surprising. But I think it's also, this work leads to some interesting questions. So let me talk a little bit about that. So when f of x is 1 over x, like I mentioned, we know that the log p bound is correct. So is this true in general? So I think this is something that would be quite interesting to study. And I have no idea how to prove like an order log p bound. I think it would be pretty tricky. In the case of 1 over x, we really use these powerful results about Cayley graphs of SL2 that are not available in the general case. And my understanding is that, I mean, really these exponential sum methods, I think, can't really be improved very much. And so really, one would need a more clever way to deal with the sort of unstructured sets, right? So as you can sort of see from this argument, you actually get a Schugers bound inequality of the correct order to get a logarithmic bound in this structured case. Really, the problem is that it's the unstructured case that's the problem, and so one would need to be slightly more clever when dealing with that. As I also mentioned, when f of x is x squared and p is 3 mod 4, we understand the stationary distribution, but when p is 1 mod 4, the associated graph seems to be kind of random, and I can sort of make some concrete predictions. So one of them is the size of the support. So there's this work on the size of the support for kind of like random graphs with degree constraints. I think I should have written this down. I think it's due to Cooper and Fries, if I remember correctly. And their work basically predicts that the size of the support, as a proportion of p, is this sort of explicit quantity in terms of some, root of some polynomial. Okay. And this has been checked on the computer. This is about like 41%, I think. This has been checked on the computer, and it seems to match. And so again, I have no idea how to prove this, but I think it is an interesting problem to just look at. You can ask another problem, which is what happens in finite fields, FQ. So again, here, one has the Weil bounds available. The problem is actually this unstructured case, right? So I really did use the fact that I was dealing with intervals here. And when you work in higher dimensions, it's not exactly clear to me what you should do, but I think it would be worth studying. And maybe I should also mention that I have some ongoing work with Pham and Max Xu on looking at higher dimensional versions of sort of the linear problem, right? So, there's this Chung-Diaconis-Graham process. It also makes sense to study that in FQ and even FQ to the D, where you look at linear bijections. And we're taking a look at that. And then finally, maybe this is something that Percy told me I should think about, which is to look at sort of the non-uniform case. Because from I think from an applied perspective, that's maybe something that's also quite interesting. Okay, so I think I'll stop there. Thanks for listening. And